Okay, this section is on polynomials of higher degree than just 2. So we're going to transform these again. We'll look at the leading coefficient, what that means. We'll find zeros, and we'll use this intermediate value theorem. Okay, so first of all, polynomial functions are continuous. They're not going to have any holes or gaps in them. Okay, this was a piecewise function. This is not a polynomial. Okay. They are going to have smooth, round turns. They're not going to have any like sharp, pointy things like this absolute value. Okay. Second degree polynomials are going to look like basic parabolas. The higher degree you get, the more flat it is here at the origin. But any even degree is going to look like pretty much a parabola. And then any odd degree is going to be like this. Okay. The higher degree you get, the more twists and turns it can have, but the general shape is going to be an odd function like this. Start at negative infinity, go to positive infinity, or unless it's reflective, which we'll talk about soon, in which case it start at infinity and go to negative, start at positive infinity, go to negative infinity. Okay, generally we call the ones with higher degree power functions. So the more general term for these polynomials would be power functions. Okay, sketch a graph of these functions then. So we can tell what these look like without our calculator, hopefully. So you can go ahead and try this real quick if you pause it. Okay, this first one's a fifth degree, so we know that fifth degrees looks something like this. Okay, you don't need to have all these twists and turns in here, but it's an odd function. Okay, now this negative sign reflects it, so it's going to actually have this shape then. Okay, so the black function is what it should look like. Just a general sketch. I don't know where the actual zeros are, but there could be up to 5 zeros. 1, 2, 3, 4, 5. Okay? There might not be, it might look like this with just one real zero, you know, and the other imaginary. But it's got to have at least one real zero, an odd function does. Okay? This one then is a parabola that opens up. It is shifted 1 unit to the left, and the general shape looks something like this. I don't know. I mean, it could have up to 4 real zeros, so it could look like this, where it's got 1, 2, 3, 4 real zeros, but it does open up, and it's a general parabola. Okay. So the leading coefficient test, basically, just like I just showed you, determines whether it's reflected or not. So a general odd function looks like this, unless the leading coefficient is negative, in which case it's going to be flipped and look like this. Okay. When it's even, when the leading coefficient is positive, it'll open up. If the leading coefficient is negative, it'll open down. So depending on all these twists and turns will depend on the other, you know, the degree, how high that degree is, and other values of b and c, for example, other coefficients. Okay, so let's try some examples then. Let's describe the right and left-hand behavior of these graphs. Let's try to do it without a calculator. So we know that the general shape of a cubic looks like this, but we know that because of this negative coefficient, it's going to be something like this. It could have up to 3 real zeros, but all they're asking us for is describe the right-hand and left-hand behavior. So to the left, we're going to say this goes to positive infinity. So the notation I'd love us to use for this, if we could, would be limit notation. The limit as x approaches negative infinity of this function is positive infinity. Now what this means, you might not use this again until pre-calc, so I won't hammer this home or make you use it. You can just say positive infinity to the left and negative infinity to the right. But what this means is as x goes negative to negative infinity over here, the function goes to positive infinity. As x goes positive, the function goes to negative infinity. So if you want, you could use at the left, it's going to be positive infinity, and right, it's going to be negative infinity. Okay. The next one, fourth degree. We know the fourth degrees are both positive infinity. We know it's going to look something like this. All right, in which case left, you'd say positive infinity, and right, you'd say positive infinity. okay? Now this fifth degree one here, it's got up to 5 real zeros. Oops. Up to 5 real zeros, it's odd. So it looks something like this, in which case left you'd say positive infinity, and right you'd say negative infinity. Okay, so these are things then that we know. I've kind of went over this, but a function has at most n real zeros. So if it's fifth degree, it has at most 5 real zeros. If it's fourth degree, it has at most 4. Okay, and then the turning points, the graph has at most, you know, if it's fifth degree, it has at most 4 turning points. If it's third degree, it has at most 2 turning points, and so on. And that's kind of what I showed you with this. You know, if it's fifth degree, we know that it could look like this basically. Fifth degree, it could look like this. Could have at most, this one has 5 real zeros. Okay, crosses the x-axis 5 times. And the turning points then, it's got 1, 2, 3, 4. So that's kind of what that all means. You know, a function, a fifth degree, this is like y equals x to the fifth. All right, fifth degrees have up to 5 real zeros and up to 4 real turning points. So n real zeros and n minus 1, because this is x to the nth power, where n is 5 in this case. Okay. All right, zeros of a polynomial function. X equals a is a 0 of the function, let's say. Then x equals a is a solution when it's equal to 0, and x minus a would be a factor of the polynomial, just like the same for quadratics. And a0 is then a point, or an x-intercept with the graph. All right, so let's look at an example. Let's find the real zeros of this and determine the number of turning points of the graph. Okay, it's a fourth degree, so we know it looks something like this. We don't know how many real zeros it has, though. It could have 4. We're not sure. Let's take a look at factorization real quick. Let's factor out a 2x squared. And left over we'll have negative x squared plus 1. All right. Now, I want to know when this thing's equal to 0 so I can figure out the zeros. Well, obviously x equals 0 is a 0. And that one's got a multiplicity of 2. Okay? The reason I know it's got a multiplicity of 2 is because it comes from this factor when the exponent right there is 2. Now I'll explain what this means in a second. Okay? The other 0 then would come from when x is equal to 1 or negative 1, right from this factor. You set this factor equal to 0, then you have negative x squared plus 1 equals 0. Subtract 1 from both sides, and you get this, divide both sides by negative 1, and then square root both sides to get x equals plus or minus 1. So the other zeros are plus or minus 1. So there's 3 real zeros here. Now if you go to graph this function then, it should look like this. It's got a multiplicity at 0 of 2, and it's got 1 and negative 1. So what it looks like is this. It goes down, it touches here and turns around and goes back up. Basically, where you have a multiplicity that's even, so an even multiplicity, like a multiplicity of 2, that means the function does not change signs there. It stays negative. So it's negative, the function's negative, 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 and stays negative. Where you have an odd multiplicity, like this factor right here, has a factor of 1 on it. So I'll show you more examples of odd later, but the function does change sign when we have an odd multiplicity. So this is a general parabola, but it's got this in the middle. And the key thing to know is that when there's an even multiplicity, the function doesn't change signs. There's an odd multiplicity, the function does change signs. So we'll look at some more examples of that coming up. Okay, that's exactly what this says for the multiplicity. When you have a factor, and k is greater than 1, it's a repeated 0 or a multiplicity of k. If it's odd, it crosses the x-axis, it changes sign. If it's an even multiplicity, then it touches but turns around. That's exactly what the book says here, so make sure you can understand their language as well. All right, last is the intermediate value theorem. Intermediate value theorem just says basically for any 2 points, there's always a point in between those 2 points. Okay? Both an x value in between the x values and a y value in between the y values. So we can use it to find zeros. So the intermediate value theorem, here's what the book says it is. Let a and b be real numbers, and then the y coordinates of those x coordinates are not equal. They're not the same point. Then in that interval between those 2 points, the function takes on every value between those. So the function is defined for every point in between 2 points. Okay, so if we look at this, we can use that idea, that intermediate value theorem, to approximate the real zero of this right here. Basically what we do is just start making a table of values. When you make a table of values, then you'll be able to locate where the zeros are approximately. Okay, let's just start with our xy table. Let's start with -2. -2 cubed gives me a -8 minus -2 squared is a +4 plus 1. -12 plus 1 is a -11. Plug in -1, we get -1 minus 1 plus 1 is -1. Plug in 0, you get +1. Plug in 1, and you get 1 minus 1 plus 1, so you get 1 still. Alright, so right here the function changes signs. We go from -1 to 1. So we can use that intermediate value theorem to determine, okay, you don't have to know the name of the intermediate value theorem, but we do need to know that the function changes sign here, so therefore there's a 0 in between here somewhere. -1 is on there. 0, 1 is on there, so somewhere in between here, the function changes values. At this point, I'll just guess and say x is approximately 0.5 then. I don't know, but this is an odd function, so it's going to look something like this, where it's going to go up and then go back up. It might come back down and touch one more spot here. I'm not sure. It might go back down beneath the axis. I don't know. But since this says the real zero, then I'm assuming there's only a 1. And in this case, that real zero must be somewhere between -1 and 1.
Oh, yeah.
And if we look at this, we can graph it in our calculator and see that yes, it does have one real zero between -1 and 0. Obviously, the easiest way to find it is by calculate 0 on your calculator and scrolling to the left of that point, hitting enter, scrolling to the right of that point, hitting enter for the third time. So it looks like it's at -0.75 about. Now, obviously, we could have kept going with our table. We could have kept saying, okay, we know that the zero is somewhere in between these 2 points. So we could have just zoomed in right here and started making more values, like -0.9 and -0.8 and -0.7 and -0.6. And it would have turned out that the closest to 0 would have been right in between these two. -0.75-ish was where the 0 was. So -0.75, 0 was about where that 0 is. So I won't ask you to know the name of this, but just keep in mind that these graphs are continuous. So obviously if one point's negative, one point's positive, there must be a 0 in that interval somewhere. It's pretty common sense. Alright, let's try some of the homework and we'll go make a homework help video for some of those questions.